So we return now to our previously discussed ideas of linear independence and span. Previously we discussed linear independence and span only in the context of Rn. We were thinking about vectors in Rn and what does it mean to take linear combinations of those vectors in Rn, and which you consider the collection of all linear combinations. And then there's this idea of linear independence that also depends on the ability to take linear combinations of vectors. Both of these ideas depend on the construction of linear combinations. We have now, though, this new context of vector spaces. Vector spaces are abstractions, right? There are lots of different examples of vector spaces that are not Rn, but they all kind of, in some sense, are modeled on Rn, and they behave in certain ways like Rn. But we're going to be discussing vector spaces in the abstract. And can we take these ideas of linear independence and span, and can we make sense out of them in the context of vector spaces? Well, as previously discussed, these ideas are all about linear combinations. And vector spaces, by design, are spaces where you can add and do scalar multiplication. In other words, vector spaces are contexts in which you can do linear combinations. So exactly what we need in order to be able to make sense out of these ideas in the context of vector spaces is exactly what we have. So we'll see that in these definitions here. The definition of the span of a collection of vectors in a vector space. Just a set of all linear combinations of those vectors. That's morally equivalent to the definition that we wrote down of the span of a collection of vectors in Rn. We're just taking that idea and applying it to vectors in an abstract vector space V as opposed to specifically Rn. Okay. Likewise, a list of vectors is linearly dependent in a vector space V if they have a significant relation. In other words, if there is a, by significant we mean a list of coefficients that are not all zero, and by relation we mean a linear combination that adds up to zero. So this too is a statement about linear combinations, and in vector spaces that makes sense. So this idea of linear dependence that we developed in the context of vectors in Rn analogously makes sense in a vector space, an abstract vector space V. Okay. Likewise, independence. Just like with Rn, collection of vectors is linearly independent if it's not dependent. Said differently, if the only relation is the trivial relation, and of course let's not lose sight of the fact that relations are linear combinations that add up to zero. Okay. So let's see an example. Let's consider the vector space of polynomials. We saw recently that this is a subspace of capital F, and so it's a vector space on its own. And let's consider the following. Let's consider the following two vectors in that vector space. Namely, P1 is this polynomial, and P2 is that polynomial. And we ask the question, is that list linearly independent? Now, at a glance, this seems nonsensical because, well, we developed this idea of linear independence for vectors in Rn. These are not vectors in Rn, these are polynomials, and that just doesn't seem to fit. It seems to be a mismatch of a question. But in fact, this makes perfect sense. You can think of linear independence in a geometric intuition way, and certainly that doesn't make any sense here, but we have a definition of linear independence here. Linear independence is a statement about relations and whether or not the trivial relation is the only relation. That makes perfect sense here. We can take these polynomials and ask, if I have a relation, linear combination that adds up to zero, if I have a relation is it necessarily the case that this is the trivial relation? Can I draw conclusions about these numbers C1 and C2? Right? This has got nothing to do with geometry. This is just an algebraic observation, an algebraic question. Okay, well, so we can take these polynomials, plug in what they are, like so. And the question can be rewritten. You know, take these terms and distribute and reorder the terms, etc. And what we find is, in order for that relation to hold, I would need this to be true. And importantly, what we have here is a statement about functions. And now let me go back and note this 0 here. This is not the number 0. This is the vector 0. This is the 0 vector. So what we mean by this algebra is not, is there a value of x that makes this equation true, that makes the left side equal to the number 0. That is not what this is saying. This is saying this polynomial is always equal for all values of x to this polynomial. In other words, this polynomial is the 0 polynomial. And there's only one way that that could possibly be true. Only if all 3 of these coefficients were 0. Those coefficients all have to be 0 if the polynomial is going to be identically the 0 polynomial. And from these 3 equations, can I conclude whether or not these coefficients here must necessarily both be 0? And well, yeah, absolutely I can. See, these 2 equations right here directly say that C1 and C2 have to be 0. And therefore the only relation is the trivial relation. And that's the definition of what it means for those 2 vectors in this vector space to be linearly independent. So we've drawn a conclusion about a list of functions that sounds like we're talking about a geometric feature of geometric vectors. And in that sense, we're visualizing these functions as having kind of a geometric relationship in this vector space.